So we are done with object-oriented programming. We're done with definitely NetBreak. Of course, a lot of you are still working on point of sale. I understand. I mean, get that wrapped up. The checkpoint is Friday. After that, if you're not finished with the point of sale project, then you'll be going on a recovery plan. That recovery plan will almost certainly include a deadline extension. Don't rely on that, but at the same time, if you can't finish before the checkpoint, don't stop working on it. You do have to finish those lecture tasks to pass the course. So make sure you're getting that eventually. But don't stress if you're getting up to this checkpoint. It's not an auto fail yet. You'll get a recovery plan with almost certainly a deadline extension, unless you didn't make your first submission until the day of the checkpoint or something silly like that, where you just clearly haven't been trying, skipped labs. There are cases where you might not get a deadline extension. But you almost certainly get a deadline extension. And then if you're hearing me say this, you'll get a deadline extension. Let's put it that way. If you're putting in at least that much effort. So you'll get a deadline extension. So keep working on that. But that extended deadline, if you don't complete it by that extended deadline, it's likely an F in the course, unless you're really, really close. And I'll review all your work and make those decisions. But after that deadline extension, if you're still not done, it might just be F in the course. So keep that in mind. Damn it. That's why that was in chat. Genetic algorithm is out. I just have to post the link. That's an important step in releasing anything. Actually had this happen in 442. I had a team that was really. I'll tell you a story while I'm doing this. I had a team that didn't. They finished their project, everything was really great with it, but they never. Ooh, what's my syntax in this? And then I just linked the other part. They had a really good project. Everything looked really good on it, but they never released it. They never made the submission to say, "Hey, we're done with this. Here's our code. Here's our repository." So I never had the submission, which at that point, it doesn't really matter what you've built. If it's not released to the public, it's basically like you haven't done anything, which is what I just did here. If I've been working my ass off getting this document ready and getting this assignment ready, but if I don't post that link, it doesn't matter. If nobody can see the homework that I created, did I ever really create it? So let's release that so I can actually get this out to you. And you can actually see what the homework is. Or else, what are we doing when you can't see it? It's like if you have a big release date, your team working on a big project, a big software project, and you hit the release date for your software, you could have the best software on the planet, this really great software, but if you forget to, upload your final project, and, if you're building a game and you forget to upload your final executable to Steam, you don't get any credit for that. There's no partial credit. You just don't have. It's like you didn't even build that thing. So let's fix that. Let's get the link live. Refresh the page and you'll see it. So let's quickly go through this. I got a lot of slides to go through today too. But let's quickly introduce genetic algorithm. Who's ready for genetic algorithm? Ooh, baby. So I'll be talking about this, throughout the week, throughout these next 3 weeks. But I just want to give a quick overview today. A genetic algorithm is can be viewed as a fancy guess and check machine. We're going to guess a bunch of solutions, check how good they all are, keep the best ones, make mutations of those and variations of the good ones, and then create a bunch of more random solutions, and then check again. Guess and check, until we arrive at pretty good solutions, usually approximated solutions to an optimization problem. So that's ultimately what we want to do. We actually don't build the genetic algorithm until application objective 1. Application objective 1 is make the genetic algorithm. And we're going to do, through the lecture task, a lot of setup for that genetic algorithm. A lot of setup for it, building cost functions, writing some statistical methods, setting up our song and playlist classes, because what we're going to be genetically genetically algorithming. I don't know. What we're going to be optimizing is playlists based on music ratings, based on songs. So we can generate playlists that we might want to listen to. The big catch to this, the big caveat, is that you cannot use the keyword var. My God, Zach, just go to the doc and scroll down. You cannot use the keyword var. You can still have values using the keyword val, but you cannot use var. You cannot have any variable that changes state. So beyond just banning var, you also can't simulate mutable state using some other method to bypass this restriction. Anything against the spirit of the assignment is going to be banned. It'll be a 0. You're not going to get credit for that, and you'll have to start over. So there are 6 lecture tasks. The structure is the same as last time. 6 lecture tasks for the right portion of the learning objective. Starts off with some arithmetic, which is getting you some hands-on experience and some experience with first-order functions and how to process data without using any variables. The first one is computing the average of a list. How do you compute an average without using that accumulator pattern from 115 where you have a variable, you iterate through the data, you sum it all up, and then at the end you divide by the length. That's our standard way of doing it in 115. Well, once I take away var, how are you going to do that? I'm also going to throw type parameters at you. What are those? How are you going to handle that? These are all good things that we're going to learn in the functional programming learning objective. Same thing, but a little more complex with standard deviation. We're going to move on to Bayesian average, which is notorious. I've ran assignments similar to this, versions of this in the past, and Bayesian average tends to be fairly infamous. I haven't done it since 2017, so it's been a while since I heard complaints about Bayesian average. It's not that complicated, but once you use the word Bayesian, certain people, it just blows their minds. So don't be one of those people. It's not too complicated. It's solving the problem. This problem that we're faced with online quite a bit whenever we have rating systems is if I have a song with 100 ratings and an average rating of 4.9 on a 1 to 5 scale, and another song with one rating, only one person rated it, but they rated it a 5. If we just use the average rating, this song with one rating of 5 would be rated higher than the song with 100 ratings of 4.9. But we all know, I know, and you know, that this 100 ratings with an average of 4.9 is a much better song, much higher rated song than the song with one rating of 5. This could be anything. This is a wild card. I wouldn't buy this on Amazon if it was a product, but I'm buying this all day even if I don't need it, because that's a hell of a good rating. So the way we address this is by adding fake ratings to every single song. And for our purposes, we'll typically add 2 fake ratings of 3 to every song, and that's going to penalize the songs with few ratings or reward them if they have one rating of 1. But it's going to kind of level the playing field and reward the songs with many ratings. So it's not that simple, not that difficult. You just add some fake ratings. I think the word Bayesian scares some students because like Bayesian statistics in machine learning is really complicated. So I think it's that word that confused them. Or maybe it was just one really loud student. It was actually a TA who constantly complained, so I think they were just in my ear a lot. Don't be frightened. It's not that scary. Parsing a CSV file with song data. A very simple task. If you could use var, how do we do this without var? That's a lot trickier, which is why it's LT4. And then building cost functions for songs. How do we tell if a song is good or not according to our cost? And the playlist cost function, how can we rate a playlist? And then finally, the application objectives, genetic algorithm, which is going to use those cost functions to generate good playlists is our ultimate goal. We have all this data about songs. How do we use that data to get a good playlist that we want to listen to? And we're going to use those cost functions to build that genetic algorithm. Yes, there are 2 application objectives. You can just, I don't know why y'all were going nuts in chat. There are 2 application objectives. Damn it, Rin. We're not making that joke every time. There are 2 application objectives. Neural networks. This one is very difficult. I think the genetic algorithm is within reach. Neural networks, for most students. Neural networks, this is a tough one. This is a challenge for those of you who want that extra challenge. Neural networks is a tough, I won't sugarcoat this one at all. Application objectives 2 is tough. If you're really looking for more challenge to sink your teeth into, and especially if you're interested in AI and machine learning at all, go for this one. If you're interested in those fields at all, this will give you a good taste of what that's going to be like. We're going to train the neural network. You'll build a legit neural network in AO2. We're going to train the neural network, which is usually the hardest part of machine learning. We're going to train it with our genetic algorithm, which is by far definitely not the best way to train a neural network. When you get into machine learning in those courses, you'll learn about much more efficient, effective ways to train things like neural networks, classifiers like neural networks. So this is by no means a really great way of doing things, but it is a way for you to be able to get machine learning experience in your second semester of computer science, if you're understanding all of the material up until this point. And I got lots of text on neural networks here in references. Please go to the references and get some good info on neural networks. And that's my very, very quick overview of genetic algorithm. Good luck, have fun. It's a good one. It's highly in demand, at least from my TAs. And it is a really nice assignment. Even it's, obviously I'm biased, but it's an assignment that it does what it needs to do by giving you practice with functional programming. And you also do something cool. Like even when I wrote my solutions, the first time I ran this assignment, years ago, even writing my solutions, I'm like, damn, I just made that genetic algorithm. It's just cool. It's just really cool. Because what a genetic algorithm does is lets you solve problems without actually solving them. You just write a cost function and let your algorithm do the rest, which is a really neat and almost a little scary feeling. There's a big conversation about that in AI, where even the developers of artificial intelligence, those machines and machine learning, even the developers don't fully know what's going on, which gets a little creepy. Things get a little bit out of your hands, out of your control. But it's neat. It's really neat and powerful when you actually code it, especially if you do the second application objective. There's some really cool stuff that the software that you write does after that. So, with that, let's learn how to do any of this. Is Towers still live? I'll check real quick. Yeah, Towers is still live. So these towers in this game, which you can go to jessehartloff.com, it was posted in chat. You can go to these towers. You notice how these towers will lead you. So if I'm moving, they'll actually hit a moving target. Unless you change direction. That's the only way to effectively avoid them, is if you change directions after they shoot, because they can't predict what you're going to do in the future. But those towers are actually shooting and aiming using the genetic algorithm from this assignment. That's actually not part of the assignment this semester. Feel free to still do it. You can pull up the old handout code. If you can find it on my GitHub, you can pull out the old handout and see my what I call aimbot. You can find my aimbot code and use that in your genetic algorithm. But our flavor this semester is song ratings. Let's get some damage on here, and I can cheat a little bit just because I understand how this works. If you walk into a wall, the towers will think you're moving into the wall, and aim into the wall. So with that, let's learn some functional programming and figure out how to do this stuff. And we're going to do that. It all starts with sorting. So sorting is something that I know you already understand. You know the concept of sorting. So I'm going to leverage that understanding and use it to explain first order functions, and type parameters today. This is something you'll notice a lot throughout your computer science career. You're going to revisit sorting a lot. You're going to do it often. And we usually do this as professors. We'll do this for exactly the reason I just said. We'll use it to motivate. We'll leverage your understanding of sorting to teach a new topic. We know you already know what sorting is. You know what sorting is from 115. And we're going to use that understanding as a foundation to teach you a new topic. I'm teaching you first order functions and in type parameters today. On Friday, we'll revisit sorting again, and I'll talk about recursion in terms of sorting. In 250, you're going to start doing runtime analysis. You're going to analyze the runtime of merge sort, which will be the third time you've seen merge sort by that point. And merge sort's on Friday repetition in 116. And I have to update the schedule. I'm moving a few lectures around. I'm moving next Monday's lecture to Wednesday. I haven't updated the schedule yet, though. And in 331, you're going to revisit merge sort again, for the fourth time, where you're being introduced to proofs of correctness. How do we prove that merge sort always returns the correct ordering? So this is something you'll revisit a lot. Every time you see sorting in a new course, don't be like, sorting, I know what that is. I can skip this lecture. Don't get into that, because it's being used to teach a new concept based on something that you already know and extending that. So let's revisit sorting. Ordering the elements of a data structure according to a comparator. We've been doing this since 115. Towers wall hacks. And we've seen this already. We've seen this when we started talking about testing and how to test lists. And this was on every interview for LO1. The TAs and I, we loved asking this one, is how do you compare two lists when the order doesn't matter? And our answer for this class was, well, sort them. This is the simplest solution to that. Sort them both and then use equal. Super easy. What dot sorted did was takes the list and creates a new list that's in sorted order. So we have two lists in this, the list that we started with, and then dot sorted is going to create a new list that we're storing in a separate variable. This is a separate reference to another list on the heap. And that list is going to be in sorted order. Oh, no lecture task today. The problem is, so that does not mean you're off the hook for today's content. This content is being tested. The problem is I need 2 lectures to get you to the point where you can even do LT1. So Wednesday's lecture will I'll likely introduce LT1 and LT2 in Wednesday's lecture. Because you need Wednesday's topics, which is on the schedule right now is next Monday. You need those topics to even do LT1. So yeah, no LT1 for today's lecture, but that doesn't mean, you know what? Yeah, it's a break. I was going to say, don't think that that's a break. You're not off the hook for anything, but you know what? If you want to treat it like that and feel good about it, go for it. So we sorted a list. This, everybody should be super familiar with this. We've been doing this since week 2 this semester. Sorted. Okay. And this uses a default comparator. So we never specified how to sort. We just say, Scala, sort this list. Just sort it. And Scala says, cool. Yeah, I'll sort it. I'll sort it for you. And that's using the default comparator. This is a list of ints. I should have my type specified explicitly here. This is a list of ints. And the default comparator, if we don't specify a comparator, the default comparator for ints is the less than function. That means that any element that's less than another element must come before that other element in the list. So negative 23 is less than negative 8. Negative 23 must come before negative 8. And negative 23 is less than all of these, so it must be the first element in the list. We're using the less than function to get our sorted order. And it's one of the big highlights today. How do we take the less than function and get our full sorted order based on a function? It's not immediately clear how that works. It's just clear that it works right now. How would you use comparator in a sense? Didn't I just do it a few times? I have a comparator. Comparator is a word we use in computer science. So what if we don't want to use the default comparator? Or actually, we are using the default comparator. What if we don't want to use the default value to sort by? So if we just do sort this list, or numbers.sorted, we're going to sort the straight up values from this list. But what if we want to sort by the default order still, but on a different value? Well, for that, we have this second way to sort things. In spoilers, there will be 3 ways that we're going to sort in Scala that are built into Scala. We're going to take these numbers and call sort by, which takes a function. This takes a function, and then each element of this list is going to have this function called on it, and whatever this function returns, that's what we're sorting by. Now, this is something I use a lot in the assignment, too, in the genetic algorithm assignment, right from LT1, where you'll have the average of a list, and it takes a function. That function needs to be applied to the list, and then whatever that function returns, that's what you're averaging. So right from LT1, this sort by is a kind of structure, kind of a pattern that I use a lot in the assignment. So sort by is going to call math.abs in this example. It's going to call this function on each element of the data structure, and then sort based on the return values of that function. You saw this in Python by setting the key when you're sorting in 115, if you recall back then. And we're going to be sorted by the output of this function. So -4, that's the least absolute value. Then 5, signs are ignored basically. And we're sorting by the absolute values by using this sort by and giving it a function. So in your homework, you'll be on the other side of this, where you'll be effectively writing something like sort by. You're going to be taking a function, calling that function on every element of a data structure to get a new data structure, and then do your arithmetic on those output data, that output data. Yeah, you can do sort by rand. It's if you want something that's not going to work so well. In some cases, sort by rand is going to run for a very long time, depending on the implementation of the sorting method. Yes, you can put your own function in sort by, and that question right there, I mean, by the end of 3 weeks, you're going to regret asking something like that, possibly, potentially, because we're going to do that a lot. Not necessarily with sort by, but you're going to be giving your own functions to methods a lot. Yeah, you don't have to sweat it out though, Roblox lover. It'll be fine. It's just you're gonna get your fill. Just like you just got your fill of object-oriented programming. You don't want to see object-oriented programming for a while. I'd be willing to bet. We're gonna get a healthy dose of functional programming throughout these next 3 weeks. It's nothing to panic about. You're gonna learn some good stuff. I can't even talk. I'm envious of you because you get to see this stuff for the first time. This is exciting stuff. Juicy content here. So what we just did was gave a method, in this case a method. I'll try to be consistent with what I call a method and function. They are very different things, functions and methods. This right here is a method because it's attached to an object. So we just gave a method as an argument to another method. And yes, we can do that, and yes, we will do that a lot over the next few weeks. So math.abs is a method defined in the math object, and we just gave that method as an argument to another method call. This method takes this method and calls it whenever it needs to process an element in this data structure. OP is fun. Wait till you see FP, though. I think FP is super cool, by the way. I don't know if that was apparent from what I was saying. Yes, we can do that, and we very slyly sneak this into 115, but we don't really highlight it. We don't really talk about it much, but you do actually pass functions in 115. Now in 116, we're passing a method, and we'll also pass functions shortly. So passing functions, which we haven't seen a function yet, but passing methods is allowed, and it lets us do a lot of different things. In our case right now, sorting in different ways. But this still doesn't get us away from the default ordering. We can modify the inputs. So here we're saying sort by absolute value, but we still have to sort by increasing absolute value. Least absolute value is always right here. We could do negative absolute value and get something different, but let's get a little more versatile here. What if we just want to shatter that default ordering completely? Like say we want to sort by decreasing value. Well, now we're going to write our first function. Any shot game today? Maybe function. We're going to write our first function, which is going to be a comparator, much like the comparators you saw in JavaScript in 115, much like those comparators you saw in JavaScript. We're going to write a function. Our first function, this is not attached to any objects. This function that's going to compare two elements of the list, and it's going to return true if the first parameter must come before the second parameter, and false otherwise, including ties. So if these can be in the same order or the order is ambiguous, this will return false. So for example, if the elements were 1 and 1, this is going to return false. 1 is not greater than 1. So a function that follows this protocol, this signature, takes two elements, where it takes two elements of the type that we're sorting. We're sorting ints here. So a function that takes two ints and returns a Boolean is going to define our sorted order. The default comparator is the less than function. So if I change this to a less than b, that'll be exactly the same as doing dot sorted. That's the default comparator. If I want something other than the default comparator, I can do sort with and give it a function that defines how I want two elements to be compared. Yeah, exactly. This is an anonymous function, because this function has no name, so we call it anonymous. So this is our first function that we defined. I should actually not include those parentheses. This right here is the function. This function, when we define a function, I want to go to the next slide. Yeah. So when we define a comparator, we have to give sort with a method that takes two elements, two values of the type being sorted, and returns a Boolean, and follows that. It should return true if the first element comes before the second one, false otherwise. So let's talk about the syntax of this function. And these, we call them first order functions because these functions can be treated just like any other value in Scala. In fact, they're actually objects. Our functions are objects. So our functions, you can ask questions like, are functions methods because they're part of their own object? I don't know. Technically, maybe. I don't know. But functions are actually objects. They're stored on the heap. We can create new functions. And I'll get to the syntax, Jack Sparrow, in Roblox Lover. So these functions are on the heap. They can be stored in variables like I'm doing here. They can be passed as arguments to functions and methods. You have a function that takes a function. And they can be the return value of methods even. You can have a method that returns a function, which we do with the score functions in the assignment. When you get to LT 5 and 6, you're writing methods that return functions. You're going to build a function dynamically and then return that function, and then you can call that function after calling the method. A lot of good stuff going on there. So let's break down the syntax here and talk about what's going on with this thing. So we have our usual assignment, declaration of a variable, and the types are a lot different here. So we have a value, we're naming it comparator, and it has a type of this, and it equals this value. So let's start with the right-hand side of the equal sign. This is the assignment, just like you've seen, your whole programming career. This is the assignment. So everything to the right, this is going to resolve to a reference to an object on the heap. Can you use custom sorting function with 2 comparator statements? I don't understand what you mean. Why would you want 2 comparator statements? Like 2 different comparators right here? You wouldn't do that. Like if you wanted to sort by one thing and then sort by another thing, you would add that code right here. You would say if A greater than B, else, if A equals B, then sort by the secondary parameter. You would add all that logic in your one comparator. So this right here, what I have boxed in, creates a first order function. This creates a first order function. It creates it on the heap, returns a reference to it, and we can work with that reference. The syntax is very similar to creating a method, except we don't use the keyword def, we don't name it, and we start right off with the parameter list. So we create a parameter list just like you would in any method, just like you have been doing all semester. Create a parameter list with types and variable names. And then you use this big arrow syntax, where a method would just have an equal sign here. A function is going to use this big arrow, this equal sign greater than. This big arrow is going to separate the parameter list from the body of the function. Everything after the arrow is the function itself. I just have a one-line function, a one-statement function. It returns A greater than B. That resolves to a Boolean value, and that's what's returned from this function. We can use a little bit different syntax here. We can use the usual brace syntax. If you have a large function, you want a lot of code, you want a lot of stuff going on in here, you can use the usual brace syntax. And then, of course, the last expression that's evaluated, either way, whether we write it like this or like this, the last expression that's evaluated, that's the return value of the function. Just like a method. Really, the only difference is this little greater than symbol right here. In fact, you can have methods using this syntax as well. You don't have to have the braces on methods either. The type of a function is defined by the types of its input and output values. Yeah, underscore is used in quite a few different ways in Scala. In general, it's a wildcard. In this case, this is shorthand that I'll start using later in the semester, so I want to give you a taste of it here for those of you watching the comment here. If you have parameters like this, you can replace them with underscores and use this shorthand, collapse all this into just this, where the order of the underscores is going to be the order of the argument, the order of the parameters. So this would be the same as A up here, and this will be the same as B up here. This will be the first parameter, this will be the second parameter. So Scala offers us this nice shorthand, but you don't have to worry about that. You got enough to think about today, and we haven't even talked about type parameters. So the type of a function is defined by its parameter types, and its return type. Again, we're going to use this parenthesis syntax for the parameters. We only include the type, so we don't need names in the type here. And then the big arrow, and then the return type of this function. This is the type of a function. The input types and the output type. So this whole line is create a variable of type comparator, which stores a function that takes 2 ints and returns a Boolean, and assign it to a reference to this function that takes 2 ints named a and b, and returns a greater than b. If you understand all of that right now, you're doing amazing. Because that's the core of what we'll be talking about for quite a bit of the next few weeks. Is this and all the implications of this, all the things we can do with this, everything about this. There's so much we can do. For example, if this equal sign were split across a parameter and argument like we do right here. So sort with takes a function that takes 2 ints and a Boolean. If we go into the definition of sort with, we'll actually find that it has a parameter of type int to Boolean. Well, it uses type parameters, which we haven't talked about yet, but it takes a function using this signature. And we give it a function that follows that signature, so the sort with works. And then sort with is going to call our function when needed. This alone doesn't... To never use var, we have to learn a few more things. There's a few more things we got to learn. This doesn't really get us closer to not using var. That's why there's no lecture question today. But once we hit Wednesdays, this in combination with Wednesday's lecture is going to start getting you there, working with data structures without using var. And then when we start talking about recursion, we'll get all the way there. Well, you'll technically never have to use var again. All right, any questions on this part right now before I move forward? Because the rest of this is implications of this and then type parameters. I never going to use var or if statements. I think you have to use, quite certain you have to use one or the other for almost every application. But you can exclude one of them. Like we'll use if constantly throughout these 3 weeks. Because there's really no other way to get around the var restriction. But it would be neat if we could restrict both of them. Maybe for certain questions you could get away without using if, but for most of what we do, like any recursion, you're going to have to use a conditional. Is there a benefit to not using var or just challenging? The short answer is it's just challenging. So for the same reason that I restricted if, when I remove conditionals, it forces you into using OOP the way that I want you to use it, because I need you to have practice with OOP. And if I let you use conditionals, by default, you're just going to try to use conditionals for everything and not use OOP, which defeats the purpose of that learning objective. You don't complete that learning objective. The only way I can really test you on it is through interviews and quizzes. I can't test your coding on it. It's just easier for you to get through the course without learning OOP if I don't ban it. Same thing with var. If I ban var, it's a very effective and efficient way to force you into using functional programming, where you might just use var and use the accumulator pattern from 116 for everything on genetic algorithm. Once I ban var, you have to use functional programming concepts. There's no way around it. So it's just used as a teaching tool to force you into learning the stuff that you have to learn in this course. There's no advantage. I shouldn't say no. There actually are a lot of advantages to not necessarily banning var, but banning state. Like the last learning objective was all about state. Functional programming is all about having no state at all. And if you don't have any state, there's actually a lot of advantages of that, because the problem with state is that the state can change out from underneath you when you're not expecting it. With functional programming, pure functional programming says nothing can have state. Therefore, we don't have to worry about anything changing on us, because it literally can't. All right. So with this comparator method, this gives our sorting functions, our sorting methods, a very high degree of flexibility. So you notice that Scala doesn't know anything about what we're going to code. Like the developers of Scala had no idea what programs we're eventually going to write, but they're able to write a sorting method that can sort anything. If I write an animal class, which was I guess this was a lecture question. So you can use your imagination here. I have an animal class. Animals have names. And a make sound method, and there was inheritance there, but that's not important to this example. But the animal class, each animal has a name, and we can sort these animals based on their name, even though the developers of Scala had no idea that this class would ever exist. And we do that using these first order functions. Scala's sort with method doesn't care what it's sorting. It just says, okay, give me a data structure, give me a list of whatever, and tell me how to compare to whatevers. And then it just does its thing by calling our function. So we get basically infinite flexibility in this method. This sort with method can sort anything. Doesn't matter what it is. Doesn't matter if it's a type we created or a built-in type in Scala. It can sort anything. It just needs a comparator and some data to sort. So here we define a method this is in the animal class, but it doesn't matter. It could be anywhere. This method takes two animals and returns a Boolean, so it meets our signature that the sort with method needs, and it's going to compare by names while ignoring case. Sort with that comparator, and we can just take this method by name, just like we did with math.abs, and pass it as an argument to the sort with method. And if we print, we get the sorting that we want. Alphabetical order, ignoring case. So Morris would be before all the capital letters. If we didn't do two lowercase, with two lowercase, we sort by alphabetical order, ignoring case. How does that work? Oh, I guess I got a little behind on time here. So let's revisit selection sort. I'll go through this quickly. You've seen this before. This is mostly, actually all review for the next few slides. So I'm going to go through this pretty quick. So selection sort starts with the first element in a list, compares that with all other elements in the list, and decides, that's right, and takes the first element that should appear. So it's going to start with 5 and negative 23 and say, which one of you should come first? Negative 23 saying, I go first. Then negative 23 we compare to negative 8. Negative 23 says, I go first. Negative 23 and 7, negative 23 goes first. So on and so forth. And then we swap negative 23 and 5. We say this, since we went through the whole list and did all the comparisons, negative 23 was either compared directly or through transitivity with every other element, and it was the one that said it goes first, so it must go first. We're going to put that first, swap these two values, and then start with the next index. Start with the next index, and then check every element. So we swap those. The first step is swapping 23 and 5. Then we start at this index, 5 and negative 8, what comes first, etc. So we go through each one, 5 and negative 8, negative 8 and 7, negative 8 and negative 4, negative 8 and 10, negative 8 goes there, swap these two, etc. Out of these, which comes first? Negative 4, swap. These, 5 comes first, swap. 7 comes first, swap it with itself. Technically, our code is going to do the swap even though it doesn't do anything. Swap 10, and then everything's sorted. So to do that in Scala, and yes, I'm going to use a few vars here. I do have a version of this in the code that doesn't use var. It's just a little bit too unreadable at the moment. It's something I can go over after a few more FP lectures, but I'm using var here just so you can actually read this code. So how does this actually work? In our code, I'm going to write this, I'm going to set this up in a similar way as sort with in Scala, in that we're going to take a data structure that is going to be sorted and a comparator that's going to compare values in that list. Now, in our example, we did ints and we did the less than comparator. And in this example, I'm using ints, but this can be any comparator. We don't care what the comparator is. We're just going to use that to ask two elements. When we went through that previous slide, the only thing we were ever asking is you two elements, out of only you two, ignoring the rest of the list, Which one of you two comes first? That comparator is going to tell us that. So we're going to do the same thing that we saw in the previous slide, just in code. We're going to iterate over all the indices. And for each indice, we're going to ask which element goes here. And we're going to call that comparator. We're going to call this comparator whenever we need to compare two values. So we don't know what this comparator is. It could be the less than, it could be greater than, it could be greater than by absolute value, it could be the difference of, I don't know, it could be anything. We don't care what it is. We're just going to call it and say if the comparator says current value comes before min found, then current value is now the new min found. This must come before everything that we looked at so far. That's the new min found, and that's the index for min found. That's it. And then it's a minimization problem from there. What comes first according to this comparator? Don't care what the comparator is, just call the comparator. If we want to call this, we'll give it our data structure of numbers, our function, whatever we want to compare by, and this code will run no matter what this function is, as long as it's a valid comparator. Like if we do math.rand that was mentioned earlier in chat, that's not going to work so well. It'll give us some ordering, it just won't be sorted by anything meaningful. But we give it a comparator that fits the protocol, and we're good. But wait, we sorted animals before, and the method that I just showed you worked with integers only. How are we going to make that even more generic so we can sort anything at all by any comparator? We want no limitations to what we can sort or how we can sort it. We want to be able to do everything. That's where type parameters come in. Instead of hard coding our method to sort lists of integers, we're going to add a type parameter which says this method can take any type. Doesn't matter what the type is. It can sort anything. You just got to tell it about a little bit about this type. So we can take a list of any type as long as we have a comparator that matches that type. Now we can't actually access any type-specific functionality. Like if this is an int, we can't take the absolute value of it in this method, but we don't have to because everything we need to know about this type, which for sorting purposes is only how do I compare two objects of this type. That's the only thing we need to know, and that's given to us as a parameter. Whoever's calling this method has to provide a function that tells us how to compare two of the thing that they want sorted. And we never care what that thing is, what that type is. We just say type. The syntax for that, we add a type parameter, which is a separate parameter list that uses brackets instead of parentheses, and defines the type or types. You can have multiple type parameters. Defines the type or the name of the type, which I just named type here. This is whatever I wanted to name it. And it's your type parameter list. And then wherever I put type, I'm saying that type matches the type of the type parameter. Maybe type should have been the drinking game. With type parameters, we often shorten this to one character. So type, often T. For maps, the types are K and V. And for example, lists and maps, any data structures, you've seen creating something and giving it a type parameter. You create a list of type something. List has a type parameter. The list class takes a type parameter, and you define the type when you create a list. You create a list of some type because list takes a type parameter. We're doing the same thing here. For our method, we're creating a type parameter. So this method can be called on any type. Just give me a list of that type and a comparator of that type, and I'll return a list of that type, which is your input list, but in sorted order. We often use one character names. I'm using T here. For a map, for example, there's keys and values in a map. So guess what the type parameter names are if you look at the source code for a map? K and V. Makes sense, right? A and B, C, those are also, common names. I like T. I don't know. It doesn't really matter. But Usually just one character names for type parameters is a convention. And now we want to sort our animals. No problem. I give it a type parameter animal. I give it a list of animals. I give it a way to compare animals that takes 2 animals and returns a Boolean. Bam, my selection sort works. It sorts these things. I have a completely generic sorting method that can sort any type by any comparator. And we often exclude the type parameter. This can be inferred by Scala. I gave it a list of animals. I gave it a function that takes 2 animals and returns a Boolean. This takes a list of type T and takes a comparator that takes a function that takes 2 type T's and returns a Boolean. Scala's like, I get where you're going with this. Like, you don't have to beat me over the head with it. Scala's really cool about this. Scala's like, you look at. I got you. You're talking about animals here. I can figure out that the type parameter is animal. So we don't always have to specify the type parameter. In certain situations, you do. If you've ever created an empty list and set it equal to a variable without specifying the type parameter, the type of that variable, Scala's going to get confused. It's usually going to give you, a list of any, because it has to guess something for the type, but it can't figure out what you mean if you're creating an empty list and not specifying the type of your variable, for example. But in most cases, it can figure out based on the context. It can look at all the context clues and figure out, okay, you're sorting animals here. I guess the type parameter is animals. T is whatever I named that. I named this whatever I want. Just like any other parameter, I named this input data, I named this comparator. That's whatever I wanted to name it. I just decided to name this one T. So the type parameter is T, and that's a type just like any other type, but it's a placeholder for the type that's going to be used when this method is called. For this method call here, T is going to be animal, so you could visualize all these T's being replaced by animal. In my int example, like if I call that with a list of ints and a comparator for ints, T would be int, and you can see all these replacing the int. This is what the method, you can visualize the method looking like if it's called with ints, all these T's turn into int. And then over time, let me just motivate the next sorting lecture for Friday. This works, but as we know, selection sort's horribly slow. My implementation is even slower than it should be because I had very terrible use of lists, and I do that intentionally to motivate lists that we'll talk about in like 3 weeks, not for a while. But I intentionally had very inefficient use of lists to show you just how slow selection sort can be, especially when you're sloppy with your implementation.